Swayam Prabha. Digital India. Educated India.
Hello everyone. So I hope you are enjoying learning actuators, which are mostly a key element in designing or using any robot. So yes, in the last class we discussed about DC motors, different drivers that can run those motors, embedded drivers also you know already, that is H-bridge driver and industrial DC motor driver. So today in continuing further we'll learn about BLDC motor. It is a motor of this kind that you can see in my hand. So it is commonly nowadays very widely used to make cobots, you see. So we'll learn about this today. So outline of today's class will be as follows. So yes, today I'll be discussing about the construction of one such motor, which is a BLDC motor. Working, how does it work? How can you convert it to an actuator basically? You know there is slight difference between motors and actuator as far as feedback and different types of sensors and transmission which is concerned with motors, you know. So yes, hardware drivers that can make it working. Demonstration using industrial BLDC motor drive. Okay. So these are some of the pictures that you see. The bigger one, the Kinova robotic arm. It is one such cobot. There are many other cobots which are there in the industry nowadays. So this is a cobot which is designed using BLDC motors, BLDC servo motors rather. It is a BLDC motor with a feedback also. There are many others like KUKA, LVR, IVA robot, UR arms and many more. We'll discuss about them also. Apart from robotics also there are many other industrial automation applications like the one you see here, electric vehicle drive. Okay, so that is a hub motor, that also is a BLDC motor, you know, and most commonly it is used like this. So one which you see here is one of the arm of a quadrotor. You commonly call it as a drone. That is that you can see here. Okay, so these are few applications which are associated with robotics and many other accessories which are there in the industry. Okay, so let us move ahead now. So yes, how do you think these motors are constructed? It is not in a conventional way. When you have an armature which goes at the center of a stator and it rotates. The way you saw a DC motor is constructed. Over here it is very much like a ceiling fan that you see at home. You have a armature which is actually rotating from outer casing of the motor. Okay, so the outer part which is there which rotates. Okay, so that is the armature, whereas the stator which actually contains the windings, okay, that is a stationary part of it. Okay, so this winding now creates the rotating magnetic field and you see magnets all around. So these magnets are fitted in the inner periphery of your rotor, which actually is going to rotate. That is the armature. Okay, and then you have slots where you can have those windings. Each of these slots, they have windings. Okay, that will create a rotating magnetic field around this one. Stator will be stationary, that will carry the rotor magnet along with it. So that is a standard principle of any motor, not just this one. These type of motors may include Hall effect sensor for position feedback and synchronous motion development. Okay, so you'll see very much in detail now. So that I'll be discussing. So because they are constructed in a way where the electromagnets, which are source of heat, because you know electromagnets are they have a bit of resistance also, not just an inductive load. So they create a lot of heat. because that is stationary, that can be mounted on top of heat dissipating element. Okay, so it can very easily dissipate the heat from the stator which is there. Okay, and then the reduced rotor inertia, because the rotor now carries only the magnets, nothing else, and mostly they are newbidium magnets, very high quality magnets. They have very good power as compared to standard magnets. Okay, so very compact form, you can get very good amount of magnetic field out of it. Okay, so they have very good torque to weight ratio. These type of motors, they have very good torque to weight ratio as compared to the similar DC motor or any other motors that you have seen so far. Okay, so yes, they are very durable. Again, you see, because they don't have any commutator or brushes which can wear off, because they continuously keep on sliding against the moving rotor. So that is the reason they require maintenance. DC motors, they require maintenance. Over here there are nothing as such. The rotor is only mounted on bearings that are very free to move. So there is hardly any friction over there, and that is the reason this type of motors are very, very durable and have very, very longer life. Okay. So yes, and the lower mechanical loading, again due to the same reason, because the rotor is of very less weight. So idle run, the rotor is not loaded, so it can rotate at dangerously high speed. But even when it is loaded, it can the rotation RPM can be controlled, and that RPM will not have any much of mechanical loading as such due to its own mass. Okay, and then they are very, very safe, this type of motor, because there are no brushes. There is no fire hazard as such. This type of motor can get into atmospheres like inflammable atmosphere, like mines or those type of locations where you can have potential areas where there are plenty of methane and inflammable gases all around. So they don't have any sparks within the motor, or the gases cannot enter into a zone which has sparks which can cause fire. So they are very, very safe as such. And because there are no brushes, there are no brushes which is continuously sliding, so it is noiseless almost. So they are very, very quiet in operation also. It is smaller dimension as compared to the power that it can deliver. So similar size DC motor will definitely deliver less amount of power. Okay, so yes, and because of all these reasons, okay, the construction is very, very simple. They hardly have anything inside apart from magnet and the fixed mounted coils. They have very less maintenance, very low maintenance, and they are inexpensive as well. So these are few applications you see, robots in flammable atmosphere. Just now I gave you an example of mines, aerial robots, because they are lighter, they are compact, they can attain very high RPM, and very good torque to weight ratio it has, so you can mount propeller on these. So this is the reason it is mounted on drones that you see nowadays. Okay, the painting robots, again the same reason, that is a flammable atmosphere. And electric vehicles, all modern electric vehicles that you see, they carry this type of motors which is known as a BLDC motor. They are nowadays with digital control system, they can be controlled to a very good extent, from low speed to high speed with a good amount of torque that it can deliver. Also in toys, hard disk drive has been using this type of motor since long time. Cobots are one of the potential application which is now coming up widely in industry also. So because these type of motors, they can directly be mounted with harmonic drives with less gear ratio also. So they are sometimes back drivable, and they allow this type of motors to be fitted directly on cobots. Okay, so yes, these are some of the application. So disadvantage, yes, because this requires a digital control system, they can be a bit expensive due to sensing and switching circuitry which are there. Okay, so yes, let us now start going into the theory, how it works. So yes, so this is the way how one can detect position of the rotor if it is there in one of the sector using Hall sensor feedback. the 6th zone. Let me just explain this one, how it works. So yes, this is the rotating magnet which is there. I want to find out where it is using three sensors which are there. One is here, one is here, one is here. So what type of signal will it give? Just look very carefully. When there are 3 bits which can assign the location of the rotor in one of the 6 zones. One of the 6 zones. Let us say this is sector 1, this is sector 2, this is sector 3, this is 4, this is 5, and this is 6. Got it? So your 0 to 360 degree is now divided into 6 sectors of 60 degree each. Okay, and you have 3 sensors. The status of each of these is digitally assigned. If your rotor is there, it will tell yes, otherwise it will say no, high or low, or true or false, 0 or 1, whatever. So yes, there are 3 bits. So if your rotor comes within this region, take one of the region as for example, if it is within this region, this Hall effect sensor is turned on. So I call it as Hall effect sensor A status, B status, and C status. So what will happen as it comes here in this zone, you see this bit goes high. This will tell you, yes, I am here. This rotor will tell you, this Hall effect sensor will tell you, whereas this Hall effect sensor is turned as 0, this is turned as 0. So what you see here is 1, 0, 0. Okay, got it? Now when you go here, let us say, so you are in sector 2, okay, so let me just, okay, now you are in sector 2. So what will happen? So the nearest region is this one and this one. So both will turn high, whereas this is totally opposite. Okay, so Hall effect sensors are mostly polarity dependent. So if it sees the north pole of your rotor, that turns it high, the south pole will not turn it high. So they are sometimes directional in nature. So these are one of those. So yes, if your rotor is something like this, this is your north pole. So this will turn this one 1, this one 1. So effectively the bit output that you will get is 1, 1, and 0. That is for A, B, and C becomes equal to 0. Got it? So now, okay, let us come to yet another zone. So this time let us say it is somewhere over any example you can pick up. Let us say it is at this zone. So what do you see? Which all Hall effect sensor will turn on? So in this zone effectively you will see this Hall effect sensor, this one will turn 1 and C will turn 1, whereas Hall effect sensor will turn, A will turn 0. So effectively you will get a bit which is something like this, 0, 1, and 1. So each one of the sector will return a value if it is represented in these 3 bits. So total 6 combinations which are possible when these they can reflect the position of your rotor, which carries actually the rotating magnet. Okay, so this will give you the feedback where my rotor is. So now you got it, yes. So if you are at a location, somewhere here, I'll try to energize a location, my field which is here. So my rotor will try to align with this. Okay, if it aligns, I will put another target. I will again align with this. Another target, align with this. Another target, align with this. So that way I will keep on rotating my magnetic field based on the current status of my rotating armature. Okay, so wherever it is, it will give you a new target in the direction where I actually want my rotor to move. Okay, so now if it is in sector 1, that is here, minus 30 degree to plus 30 degrees. So this one I am talking about, this one. So what will happen? So if it is here in this sector, So what I am doing, actually making, because the rotor is already here now, okay. So this time switching this one on will not help. I want to move it, let's say this direction, okay. So what should I do? I should switch on my electromagnet, which is a pole here, opposite poles which are here, so that if C is turned on, C bar is turned off. So in that case, this will be high and field will be directed like this. Now, because I want to go to a next location which is somewhere over, I want to make my rotor something like this. So what I'll do, I'll quickly make this one high and this one low, okay, so that my field is directed something like this, okay. So this will take my rotor in this direction. So it moves from sector 1 to sector 2, got it? So this is how I can keep on energizing. So what happened, I made this one 0 0, A and A bar as 0 0, whereas C bar is made high, and C is turned low. C bar is made high and C is turned 0, got it? And I have also made this one high. So this time B is high, B bar is 0. So this is high, this is low. So you have high here, you have high here, you have low, you have low. So effectively the resultant magnetic field will try to pull this rotor towards sector 2 and sector 3, somewhere in between, right? So you try to create a maximum magnetic field where you want to go, got it? So this is from going from sector 1 to sector 2. Now let us come back and see how to go from one of the sector again to another one. This time let us say I am somewhere over here where my rotor is shown here, okay. Let us say I am here. You tell me, you just analyze by looking at this, how should I do my job then? Okay, now that it is already in this sector, that means it is already seeing this position. So I should make B and B bar both equal to 0. B and B bar. So it is in sector 3. It is in sector 3, which is from 90 to 150 degrees, okay. That is another 60 degree sector, this sector, okay. So this time it is here. So now what I am going to do, so I'll switch on the next pole, okay, the next pole. So which one is there? That is A dash. A dash should be high and A should be low. Why? Because this will create a next target magnetic field which is like this. Another one, so yes, this will because I am here, I am making A bar high and A as 0, okay. This creates a field which is like this, and also I can make this also as high. That means C is high, C bar is low. C is high, C bar is low, okay. So C is high, C bar is low, got it? So this is how I am trying to create. So effectively it will create a next moving target. So this will create a resultant field which is somewhere here. So this will pull my rotor to the next sector, okay. So this is how I keep on changing my targets, you know. So now you can be somewhere where you don't have any existing field, let us say. So let me just be in one of those locations now, okay. So this time let us say I am somewhere in this location already. I am somewhere like this. I am in this sector. So again what you can do, so this sector is represented by 150 to 210, this one, okay. So if you are already here, that means A bar and A should go to 0. This is 0. And which one should be high? You should be C and C bar. So that means C should be high, C bar should be low. So you create a field which is something like this, and you have to make this one high as well. That means B bar is high, B is low. So this is high, this is low. So you got it. So that means B bar is high, B is low, and C is high, C bar is low, effectively it creates a target which is something like this. So this will pull my rotor to this field. So hope you got it. So based on the location feedback which you saw it here, I can keep switching my coils. I can keep energizing my coil. So poles are, there are 3 pairs of pole, okay, A, B and C. Those are connected in a way, I can draw it here. Okay, I have a pole which is here, I have opposite pole which is here. So I can directly wound it in a way like, so effectively if I pass current like this, this becomes north, this becomes south. Okay, so if I pass my current which is something in a different way, okay, so if I try to pass current which goes like this in a reverse way, okay, so in that case what will happen, this will become north and this will become south. So that is the way you can flip between, this is C bar and C if it is. So this we call it, okay, this we call it as C, so this is called as C bar. Got it? So this is the way you can do switching off all the coils. Okay, so that is how it works. So how this type of motors are connected, let me just show you. How can you make one wire which is there positive as well as negative, a single wire. So there is an arrangement, two switch arrangement. So let us say you connect it like this. So this is your high line and then you have a ground wire which is over here, black wire. Okay, so now I want to have some arrangement where my single output which is here is to be made high or low. So there is a way to do it. So if you have an alternative which is like this, there is a switch here, there is another switch which is here. Okay, so this you may call it as A and A bar. Okay, A and A bar. So what will happen, you see? So if you switch this one on, if you switch this one on, what will happen? Okay, so this is your positive line, this is your negative line, this is your positive line, this is negative line. So if you make this on, this becomes positive. Got it? So if you turn this one off and make this one on, so what will happen? This will become a negative one. So this is how. So now you have an arrangement here, you have a very good arrangement here. Instead of switching on and off, you have two transistors. As you know, transistors can be used as switches. So you have transistor 1, you have another transistor which is connected to ground, this is connected to supply. Let me wipe off rest of the things. Okay, so this time what I'll do, I have a control wire that can trigger this, switch on this circuit, this transistor 1 and 2. So this is A transistor, this is A bar transistor. Okay, now your wire is connected from here. Okay, so what will happen? If you switch A high, this will become positive. If you switch A bar high, this will become negative. Okay, and then you have 3 such arrangements. So you have one more transistor pair which is here. Okay, that is connected to ground. You have yet another one that is connected like this. Okay, and you have this wire and this wire, 3 different wires. So this is known as B, this is C, this is B bar and this is C bar. So you see what we can achieve by doing this. So each of these wires, this one and this one, can be made high or low. Okay, so now you look at this figure, what this is trying to do. Now you have 3 different coils. So how you were switching each of the wires polarity, as you know, that you required somewhere here. Okay, you needed A and A bar to be high and low or high, whatever. So that is done using this. So if you mean A is high, if you want to make A high, so you have to make A high, so you have to make this switch high. So if you want to make A bar high, you have to make this switch high. Got it? So A and A bar are oppositely placed, and you know this type of winding is done using star wiring connection. Okay, so you have at the center all the coils are connected here, and you can feed in from different directions. So now if you want to make coil B and B bar are there, so if you mean B high, you have to make this high. If you mean B bar high, you have to make this one high. Okay, B and B bar both cannot be one at a time. Yes, both can be 0 at a time. Okay, but both cannot be one. So this creates a waveform which is very much like this. But yes, now let me give you another very good example here. Let me go to my whiteboard once again. You see this all the 3 wires are connected like this. You have first wire which is connected like this. You have another wire which is connected like this. You have yet another wire which is connected like this. You see what is going to happen if current comes to one of those. Okay, it has to go out from remaining 2. Okay, it has to go out from remaining 2. Okay, so it can also happen, it can also normally in a star winding, you have connections which can create something like this. Okay, so if one of them is sinusoidal like this, so another one could be, if V is equal to E0 sine omega t, so what could be the other one? Other one is V0 sine omega t plus 120 degree. Effectively, it should create a shifted waveform by 120 degree, so that resultant of sum of all the 3 currents is always equal to the actual supply which is there. Okay, that is the maximum value which can be there. So sum of all those will always be equal. So that means if it is going from here, so equal amount may be distributed to both of them, so that outgoing from this junction should be equal to incoming to this junction. You remember your Kirchhoff's law also. So yes, so that is how it works. So this is how it works. So effectively it will create a field in one of the direction, right? So this is how it is connected. So it is effectively trying to simulate a 3-phase winding, to all these coils. Okay, so yes, so this is equivalent to, let's say, a sinusoidal figure. Okay, so another one is trying to create another sinusoidal figure which is something like this. Yet another one, this is trying to create another sinusoidal figure. The overlap altogether, they are sine omega t. One of them is sine omega t, next is omega t plus, next one will be sine omega t plus 120 degree, third one will be sine omega t plus 240 degree. Got it? So effectively these are the 3 wires that are to be there. So we cannot generate this kind of signal for a DC motor. So best way to do that is a trapezoidal way. That is what you have seen here. So the best way to do that trapezoidal way is the nearest one to the sinusoidal way. So this is how these switches are done. Yes, these switches are not just switches, they are transistors. So they can MOSFET or transistor which can gradually take it to this level. So negative to plus, stable there, come down gradually, be there, come up gradually, be there, like that. So it is nearest to the sinusoidal waveform. So each of these has got 3 phases. So vector sum of all these should be equal to a constant. Okay, that is the constant field. So that keeps on rotating. So that creates a rotating magnetic field. So if you provide a 3-phase, so this is not exactly a constant rotating field. There is a bit of hump because of DC characteristics here. Okay, so I hope you got it, how to create a rotating magnetic field. Okay, so this is what which goes. So there are many dedicated chips. One of them is HIP 4086. So it has a similar connection, so it can trigger the switches which are there. You see, you have one switch A, B and C, you have A bar, B bar and C bar. Okay, this is to check any reverse polarity which is happening. Okay, so all these are connected by the 6 wires which are coming from the controller which is here. So they can easily control the 3-phase current which goes to the winding of these coils. Okay, so that is what is creating rotating magnetic field, and finally your rotor is following the rotating magnetic field. Okay, so there are many this controller has an input which can come, that is through a potentiometer, you see. So this potentiometer gives you a voltage signal to this controller finally. So that is finally controlling the speed with which that actually determines the omega. So if I say sine omega t plus whatever angle is there, so omega is controlled. So the rate at which this field rotates depend on this. So speed can be controlled, and you can even make your field go counterclockwise direction. If you are moving in the clockwise, you can also go counterclockwise direction. So both the direction, the speed, both are easily controlled. In order to control raw position at least, you can just take the feedback from the sector region that you saw in our initial slide, somewhere over here. Using Hall effect feedback, you can very well get the sector feedback where my rotor is there. This also, if you take analog reading from your Hall effect sensor, you can, not that precisely, but you can get an estimate of where my rotor is. Okay, you can make a feedback control system to stop your rotor exactly at the place where you want to go. So you can also do position control based on these Hall effect sensor, but yes, they are very coarse in nature. They are not very precise. In order to make it very precise, you need to have a dedicated feedback mechanism like a potentiometer, or maybe a magnetic encoder, or maybe optical encoder, or those kind of stuff. Okay, so that will give you a precise feedback and precise positioning control as well, apart from this. So yes, I have this Beckhoff 7411 BLDC motion interface, that is the driver, which can do this task for you. In industry, this kind of controllers are there. So this can run at 0 to 8 to 48 volt DC with maximum RMS current that it can give is 4.5 ampere via power contacts which it has. Yes, this is the power contact which is here. PWM clock frequency, that is the frequency at which it can do all sorts of control, is 16 kilohertz, which is quite high, so you hardly see any hum or noise over there, and they are very precise, that is the reason. And minimum winding inductance, which the kind of motor should not have more than this inductance. So you see, you have inputs for various reasons. You can have end sensor, so end position can be taken up. You can have feedback from the encoder, that is Hall effect sensor, or from the encoder you can take up. And you have fan diagnostic. There are fans which are fitted somewhere in this location that will cool up this one. If any defect goes with those kind of fans, so it will give you a feedback, yes, now I am faulty, don't feed me with too much of signal, I may fail. Okay, so you have 3 for Hall effect sensors. You have 3 for Hall effect sensor that you can feed in. So this is a encoder, which is an externally mount encoder for precise control, whereas these 3 are dedicated sector sensors, that is Hall effect feedback of the inbuilt which is there in your this kind of motors. Yes, output, so it is 1 for BLDC motor, that is phase, all the phase wires which are there. Okay, 3 UVW. Okay, and then you have 1 for fan mode, 1 for sensor supply, 1 for encoder supply. So all the outputs goes to the different attachments which are there in the motor. That makes it an actuator, you know. So yes, isolation, it has 500 volt isolation, IP20, reverse polarity protection, and so on and so forth. This is exactly the same configuration which I have used for my other driving tests also. So yes, I'll follow this one, this driver. This is the motor, which is not a very good one. It doesn't have an external encoder here. It only has Hall effect sensors. Okay, made by Tachometric Control, SM60. The data sheet is online. You can see, I'll share with you. It has 3 Hall sensor outputs also. Maximum speed, it is 60 watt, 12 to 24 volt DC, 3 ampere current, 4 poles, IP44 and so. So IP44 is the type of protection it has. So now it is connected like this. So whole of the system is very much the way I have used for stepper motor and DC motor, you have seen already. So this is the only change which is here, that is EL7411, the one which you saw here, EL7411, the same one goes here. Okay, so that is the additional stuff. So here are all the kind of UVW are the phase wires, over here UVW for the Hall effect sensors. Okay, and then you have motor phases, which is UVW here, Hall W is here, Hall supply is there, Hall effect sensors, they need supply also, that comes from here. Okay, and rest everything is same. This is your twin cat communication which is happening from your PC. This is your HMI, this is your HMI, this is your UPS, this is power supply, this is EtherCAT coupler here, and this is your filter. Got it? This is the real hardware layout. So this is the motor which I want to run. Everything is similar to the one we have seen already. Okay, the configuration is very similar to the way you have to have a twin cat system here. So you open a new project, you search your system from here, select your system, search for the connected IO boxes. So here you have your motor driver, which is this one. I could find out, I have declared a object with one of the variable which I want to change. I have connected this object to the axis, and this is the parameter which it can give you as a feedback, as a status, whereas these are some which I can control. Okay, so this object has got some variables which can be accessed from external environment. I have used Python. So let me just run that Python code here, and you will see it running. Okay, so you see how it is run. So you see, I am trying to do some coarse position control. Okay, even with the coarse position control, it is almost accurate. You see, it is trying to go to exact positions like 90 degree, 0 degree, 180 degree, and so on and so forth. So it is able to go to different locations, almost, not exactly, but yes, it is able to do such controls even with the Hall effect sensor feedback. So Hall effect is digital in nature. I can use it as high or low to sense my location, but sometimes Hall effect sensors values lets you know the precise location based on the analog input from all the 3 directions. Got it? So that is how it is made to run. So positioning is done. You can also do velocity. There are inputs for velocity also, you can see in this code. So yes, that velocity is also fed. So I want to go to a position with this much of velocity. So I get continuous feedback of position and rate of change, that is the omega that I told you. So that is what is changing the speed. Okay, so speed and position both are controlled here. Okay. Okay, so you can repeat it later on. So that's all. Thank you for this lecture. In the next class, I'll be discussing on AC servo motors, which really goes on to industrial robot. That's all. Thanks a lot.